In this question 7, we have some long chain alkanes. This is 4-methyl heptane. If you try to put number here, 1, 2, 3, 4, 5, 6, 7. How about if I go the other way? 1, 2, 3, 4, 5, 6, 7. It looks like it is symmetrical. So whether you go from left to right or right to left, this blue or pink color will put the branch group, which is 1 carbon methyl CH3 there at position 4 regardless. When we do cracking is defined as the breaking up long chain hydrocarbons into shorter chain hydrocarbons, which can be a mixture of alkane and alkenes, because these shorter chain hydrocarbons are more valuable, they are more in demand. So state the conditions, plural there, for cracking to happen. Usually the cracking we are referring to will be catalytic cracking. So when you think about catalytic cracking, we use things like Al2O3. You can use SiO2 as a catalyst. So Al2O3 or SiO2 as a catalyst. And you also need high temperature, but not as high as thermal cracking. This one can probably happen at, I don't know, 500, 300 degrees Celsius, but definitely high enough temperature to force it to happen, as you do need to break covalent bonds, and that is just being helped. The rate of reaction is being made faster with the use of the catalyst, obviously. Okay. Suggest the structure of B. B is C3H8. It is still a hydrocarbon. We have just broken the 7-chain hydrocarbon into a 3-carbon hydrocarbon. I can be thinking about C3H8, CH3, CH2. Is that correct? CH3, CH2, CH3. Yeah, 3 plus 2 plus 3 is 8 hydrogen. It's entirely possible. It cannot be alkene because there are too many hydrogen there. It's CnH2n plus 2. The structure, they did not mention skeletal or display or structural. So, you can do skeletal, structural, or even display. You still get the 1 mark there. On to the next bit of the question. Compounds C, D, and E are isomers. They don't tell you what kind of isomers, whether it's structural or optical, you don't know. But they are C5H10. Most likely they are alkene, CnH2n. In fact, the next bit is chemistry of alkene. This is AS, and chemistry of alkene. This is to do with oxidation of alkene. And this is extreme condition. Concentrated acidified KMnO4 is going to be the extreme condition. And when you get the extreme condition for the oxidation of alkene, you're going to get the rupture of the carbon-carbon double bond. When we get CO2, that indicates you must have a CH2 double bond like this. This is what you call terminal. Terminal CH2 will give you carbon dioxide. Now you also get this compound F, which have 2 oxygens. There are 2 other possibilities you can have in a double bond. That was the first possibility. The second possibility is when you have RCH double bond, that will give you RCOH and a oxygen there. So you get a carboxylic acid from a RCH double bond. Continuing upwards, when you have RCR like that, so you have carbon of the double bond bonded to 2 other carbon. Here is carbon of the double bond bonded to 1 carbon and 1 hydrogen. So when you have 2 carbon there, what you're going to get will be ketone. When you oxidize the alkene there, you're going to get a ketone instead of a carboxylic acid. The very fact that we have 2 oxygen there would mean it cannot be a ketone with 1 oxygen. It has to be a carboxylic acid. So F must be carboxylic acid. F must be carboxylic acid. And if F is carboxylic acid, what does that tell us? That F comes from RCH double bond. F must come from RCH double bond like that. Now what is the next bit of the information? D and E are also alkene. They give a 1-to-1 mixture. 1-to-1 mixture of G and H. So G is 2 carbon carboxylic acid because again 2 carbon, and then H is also 2 carbon, cannot be ketone. So G and H must also come from RCH. So again G, H, and also F, they come from RCH double bond. They give you carboxylic acid. Okay, which means G and H are carboxylic acid. So what do I know so far? G is probably the easiest one to think about because 2 carbon carboxylic acid, it must be ethanoic acid. A 2 carbon carboxylic acid, no other choices. They want to suggest structures. They did not mention display, skeletal or structural. My tag is always draw skeletal because it's fast, it's elegant, and you're expected to be able to do it. CH3, carbon from 4 bond. There's one there, 1, 2, 3. CH3, CO2H. The next thing is this 3 carbon carboxylic acid. So H must be propanoic acid, and H is 3 carbon carboxylic acid. You cannot isomerize 3 carbon acid because it's not long enough to branch out or anything. There can only be one answer there. If D and E are the alkenes that give you G and H, and you get 1-to-1 mixture of each one of these from this alkene, that means D and E must be isomeric. D and E are most likely going to be cis and trans isomer. If I have RCH double bond, let me label this as like the pink one, and then this other one as like the black color one. So if I have the black color one, and then the pink color one, and then the pink color one, and the black color one, like this. So I'm going to write in the carbon-carbon double bond. Okay, and then I would draw what happened on the other side. Now, if I have RCH double bond, so this is the carbon of the double bond, I must have RCH in order to give me carboxylic acid when I oxidize the alkene as chemistry. So that means I must have a CH3 on one side, carbon bond to carbon. The hydrogen is not bonded to carbon, so the carbon bonds to carbon, and I have a hydrogen on one side. This is 2 carbons bonded to the carbon in black, so I have a CH2, CH3, that is the CH2, CH3, RCH. When I break this double bond, RCH will give me a 1, 2, and 3 carboxylic acid, propanoic acid. This is the 2 carbon there, 1, 2, so RCH will give me a 2 carbon carboxylic acid, ethanoic acid upon oxidation under extreme condition. These 2 groups are on the same side of the carbon-carbon double bond. This is going to be your cis. This is going to be named 1, 2, 3, 4, 5. If you go the other way, you have 1, 2, 3, 4, 5. So pen 3 in is a bigger number than pen 2 in. This is cis pen 2 in. They haven't asked you for the name, but D is cis pent 2 in. And then E must be the trans isomer, where the 2 alkyl groups must be in opposite position. I'm just going to draw the CH3 there and the CH2 CH3 there. So I just put the H there and there. When you break the double bond, they are still going to give you the same product. RCH will give you this. The RCH here will give you that because 3 carbon give you 3 carbon carboxylic acid from the RCH. The 2 carbon RCH give you the 2 carbon carboxylic acid there. Okay. Now compound C gives CO2 and this 4 carbon carboxylic acid. What do I know about compound F? If I draw it as a carboxylic acid, 1, 2, 3, and 4, it could be branch. Do we know whether it's branch or not? We have no idea whether it is branch or not. We just know it's shorter chain hydrocarbon. We have no other information whether it is this, or you could of course also draw the branch isomer, which is this one, because when you have 3 carbon straight chain like this, you can branch it out into like that, and then you will get 2 methyl propanoic acid, or you can get butanoic acid. It's perfectly fine, but whatever you draw there must correspond to the actual alkene. So if I have my actual alkene, I must have H and H, because this CH2, terminal CH2 will give me CO2. This carboxylic acid comes from RCH. The fact that I have H and H, they are the same atom on one carbon of the carbon-carbon double bond. That means I can never have cis and trans isomer. So it doesn't matter where I put the alkyl group on top and the bottom. It really does not matter, because this side already tells me I cannot have cis and trans, because 2 atoms or 2 groups of atoms, they are the same on the same carbon of the carbon-carbon double bond. No cis and trans there. So I want to get 4 carbon carboxylic acid. So this is CH2, CH2, CH3, 1, 2, 3, and 4. So 4 carbon carboxylic acid, 1, 2, 3, and 4. Okay, RCH, carboxylic acid, CH2, give me the CO2. You can also get from this other one. So this one will have come from, if I draw the other one, or F comes from, what is the alkene? Terminal alkene. And then I will have 3 carbon like this. So this is the RCH. So this is carbon 1, carbon 2 is branch, and carbon 3. So this will be your C if you choose to write this branch isomer of the carboxylic acid. You must get this for C here. But if you do this straight chain, you must get this. There are really no information on whether it is straight chain or branch chain. Just from this alone, we don't know. Okay, we do know it's C4H at O2. This is CH3, CH2, CH2, CO2H. So there are 3, 4, 5, 6, 7, 8, and there are 2 oxygens. This and this, they are what you call chain isomer. And you will see that this one is CH3, CH, CH3, CO2H. So again, there will be 3, 4, 5, 6, 7, 8. 8 hydrogen, 4 carbon, 2 oxygen, just like the formula of F for this one here. Because they are chain isomers, same molecular formula, different structural isomer. Between D and E, so D and E must be your geometric isomer, the cis and trans isomerism. Okay. Now propene is an alkene. It reacts with bromine to give you 1,2-dibromopropane. So you know that it will decolorize bromine water. And what you get is you add bromine across the double bond. The type of reaction is what you call addition, as stated in AS introductory. The mechanism is what you call electrophilic addition. Be very careful about the type versus the mechanism. Now they say, how is it carried out? How is it carried out? In the dark? Because if you do it in the presence of sunlight, you might do free radical substitution instead on the alkane. Instead of this addition reaction, your bromine will still get decolorized, but it might react with the alkane instead of the alkene. What is the type of reaction? It is an addition reaction. They are not asking for mechanism. You shouldn't be confused here. You shouldn't write down the mechanism when they ask for type of reactions. Have a look at the AS introductory organic chemistry syllabus there. The very last 2 marks of these questions is all about mechanism, which is the electrophilic addition mechanism. So now they want you to draw the electrophilic addition mechanism. If this is an AS paper, they will probably give you 3 marks or 4 marks already. We need to be careful of what we're doing. So if you want, you can draw a display. They are not so big, but typically I usually just draw my skeletal formula. Doesn't matter. The first thing that happens is the Br2 molecule is actually non-polar, but when the Br2 comes close to the double bond is rich in electron, and they will polarize this one to be delta plus, because this now become electron poor. As this is rich in electron, you want to attack electron poor center there. So the first thing that happens is rich attack the poor. The rich in electron is the carbon-carbon double bond, attacks the electron deficient bromine, and then break away and give the 2 electrons to the bromine there. So everything else doesn't change. But what changes is you have added bromine. Then you have a plus there. But you know better that there could be 2 possibilities actually. That is 1 possible carbocation. But I could also get the other possible carbocation. That is going to be where the carbocation is on the other side. So I'm going to remove that Br there. So what happens is the Br add on the other carbon and I get this. Is there a difference between these 2? There is. Okay, this is a primary carbocation because the carbon with the positive charge is bonded to one other carbon is a primary carbocation. This one on the right is called a secondary carbocation because the carbon with the positive charge is bonded to 2 other carbon. This, however, will not give you a different products. They will give you the same products because you are doing the reactions with a symmetrical Br2. So from the lone pair of the Br minus, attack the carbon. From the lone pair of the Br minus, attack the carbon. The Br minus come from here. The 2 electrons go to Br. You have a lone pair. No charge and no charge. Now a carbocation is balanced out by the charge of the Br minus. So altogether, you are going to get the final product. Let me just copy paste what I did before. So that was what you gotten. And now I am just showing you the other Br adds there. But of course, the other Br could also add there. So, I better just use a same color so that you are not confused about what is happening. So you get the same product whether from this primary or secondary carbocation. But in general, we said that tertiary carbocation is more stable than secondary carbocation is more stable than primary carbocation. You will know this from your AS chemistry as part of the stability of carbocation. This is called stability of carbocation increases as the number of alkyl electron donating groups by inductive effect. They are all as stated in the AS syllabus. Inductive effect is under alkene chemistry, and the stability of the carbocation will increase due to more alkyl electron donating groups by inductive effect. Doesn't make a difference here, but it will make a difference when a question gives you major versus minor product. It's just a very straightforward 2 marks mechanism. I'm sure you won't get penalized if you don't draw the other intermediate, but you still need to show rich attacking the poor, the dipoles, the lone pair on the Br minus attacking the carbocation, carbon, giving you the final product to complete the 2 marks mechanism there. And that's the end of that 10 mark question.